Hey everybody. Thanks for your patience and bearing with us. How's the DevFest treating you all? Learning cool stuff?
Yeah.
Getting over your lunch coma? So we're going to be talking about Kubernetes runtime security, which is a branch of security stuff. It's important too, that people often overlook when they're doing their security planning. So this will be more, this is like probably 70% security, probably 30% Kubernetes. But before I get into that, let me tell you a little bit about myself. Hi, I'm Jen. Hi. I'm a security advocate at Google, which means I spend a portion of my time doing security research on my own, like independent stuff. I spend a lot of time working with other security engineers, doing fun security engineering stuff, learning stuff. Like my background is software development, so it's been a transition for me in the last couple of years. And then I learned things that I would love to have known when I was doing software development. And then I bring these lessons back to all of you so you can write software that runs safer and is better when it's, it's not getting code. I always love hearing from people. If you'd ever like to reach out to me, questions, comments, especially about Google Cloud Platform, the security stuff. My DMs are open on Twitter, and that's probably the easiest way to reach me. And if you'd like me to reach me via some other means, there's links on my homepage. There's also slides to this talk. Okay, let's get into it. So first, we're going to start with a short story. It's a story. It's a true story. This happened back in 2018. Tesla was running a Kubernetes cluster. Yay, it's cool, Kubernetes, right? And something bad happened. They realized that their Kubernetes cluster had been pwned and that it was being used to mine cryptocurrencies, which is actually about as not bad as that could possibly have gone. I don't think the hackers knew that they had compromised Tesla. They probably would have gone after some secret information. Instead, they just used their AWS account to mine a bunch of cryptocurrency. So Tesla kind of dodged a bullet here, but it's still probably a nightmare to deal with. What happened was they were running a new Kubernetes cluster, and they had a fabulous Kubernetes dashboard, which is a really cool tool. It tells you all sorts of useful information. But what you don't want to do is you don't want to expose it to the internet without authentication. And you don't want to run that on a server that has privileged credentials for your cloud provider on it. And that's what happened. They had the dashboard up. It had a vulnerability in it. Vulnerability got taken advantage of. They got some AWS credentials. They used that to spin up a whole bunch of VMs and cost Tesla a bunch of money. And they could have done a lot more damage. So in other words, like vulnerabilities that are specific to Kubernetes are a real thing we need to start worrying about now. Before you go and you roll it out into production, you want to at least put some thought into this. You want to do some planning early so that you make sure that you end up in a safe situation and you don't repeat mistakes of people before. So we learn from the mistakes that happen. So here's what we're going to be talking about over the next 35 minutes or so. First, we're going to do a kind of a container security overview. Then I'll spend some time talking about, let me just take a sec. I'm not sure I opened the But this is an overview. Okay, never mind. Sorry. Bear with me. I grabbed a slide. I guess it's slightly different than the slide deck I thought it was. But that's okay. I'll present this one. Then we're going to spend some time talking about the threat. I think this one will probably be more useful for people who are interested. I actually don't know what talk I was replacing. Oh, no, I moved again. Thank you. I don't know what talk I was replacing. Actually, I guess I should ask that. What talk was supposed to be scheduled for now?
A DevOps data mine managing microservices and databases.
Managing microservices and databases. Cool. Okay, so a more overview of Kubernetes talk. Then I need to dive into the specific Kubernetes talk. Okay, this will actually be more appropriate for all of you anyway. But before I get into the agenda, I'm actually going to survey all of you some quick questions. How many of you are running Kubernetes in production right now? A couple people. How many of you are security engineers? Oh, I apologize ahead of time for all of the generalizations and other mistakes I made. We'll talk about it afterwards. How many of you are software developers? And how many of you kind of wear the DevOps, SysOps, etc.? You run a software. Oh, I like that a lot of people are interested in that. That makes me really excited. Cool, thank you. That'll help me kind of like steer this a little bit towards there. Okay, so we're going to spend a little bit of time on a container security overview. A little bit of time talking about the threat model, because when you're doing security stuff, threat modeling is something we do at the beginning to figure out where we should be spending our time to protect things. Then we'll be talking about software supply chain and a common way to protect your systems and make sure you don't accidentally deploy somebody else's vulnerable code. And then we'll be talking about my favorite topic, which is actually the deck I thought I had pulled up, which is runtime security. First, let's do an overview of container security, or rather a container overview from a security perspective. Containers are really cool because they're super dynamic. Sorry, I'm going to step back again. Okay. Oh, I did it again. The other one. This one. Presenter. Containers are really cool because they are dynamic and we can kick them up and destroy them all the time, which has some advantages on our ability to deploy services. It's kind of like all the promises that virtualization made many years ago, except it really works. I can actually make it so that my software will kick up new containers to handle load on the fly. I can make it so that my applications will roll releases really easily, and this stuff like actually works without a lot of heavy weight behind it. And a lot of the reasons it works that way is because we have changed the way we work a lot from previous virtualization models. See if I can get that bar to go away. Previously, when we would deploy virtual machines to physical hardware, we'd have our physical hardware on the bottom. We'd be running a full-blown host operating system that you could probably log into and use like as an operating system and install applications on. And that would have a hypervisor as a feature, or you'd even be running it as an application in user space. And then you would have a whole bunch of virtual machines. Each one of them was running their own full guest operating system. And then the stuff you actually cared about to get your features to your customers, you had all of the binaries and libraries that you depended upon, and your actually application code that you and your organization wrote running on top, or software you might have purchased from a vendor. In container land, we have stripped away a lot of the stuff that seemed to be unnecessary before. We still have the same underlying hardware, because everything's eventually got to run on a CPU at some point. On top of that, we have a host operating system, but now we have a new breed of operating systems that are just focused on running containers. A lot of these things don't even have a shell, so you can't even log into a lot of them. And this is really cool and has a lot of benefits because from a security perspective, you have a much smaller surface of attack, which is great. They're easier to protect. A feature of these operating systems is they have container runtimes, which allow you to run containers. They're separate user spaces running on the same kernel. And now we can see that a much larger portion of the system is actually dedicated to the binaries and libraries we care about and the applications that we want to run. So they are different, and there are pros and cons of each side from a security perspective. From the attack surface side, which I've already alluded to, containers have the minimalist host operating system and very small guest operating systems too, which limits the surface of attack. And by this I mean that there are fewer things running on there that would surprise you. Because those things that are running on there that you don't use and you don't care about are usually the things that end up getting targeted because they're the things you're not patching very often. Like for example, there's probably not a mail server running on them, which is good because mail servers get hacked all the time. They're hard to run in a secure way. But the flip side is that virtual machines provided, the hypervisors that these virtual machines use actually provided a really strong security boundary. Because I had a separate kernel running for each one of those VMs, it protected me against a different set of exploits. So there's a little bit of a pro and a con here. Which one's actually better? It's hard to say. It depends on your circumstance. Right now, based on the kind of exploits that are going around, it's hard to say still. It depends on circumstance. Okay, let's talk about isolation. So isolation in terms of kind of the noisy neighbor problem and the resources that the clients are taking. Within virtual machines, you actually don't have as much control over isolating resources between those different hosts. Like if something gets really hungry, it's often going to be able to use a lot of those resources. But, and it's often hard to manage the resource consumption from that perspective. On containers, on the other hand, built into the same
features that made containers work, namespaces and C groups, we have fine-grained controls over the resources that we provision to our containers, which gives us the ability to give very specific amounts of like CPU usage and stuff like that, much more fine-grained controls of resources than we had with virtual machines. So containers are kind of a clear winner here. Next, root permissions. So in virtualization or in VM land, there was actually a very small set of system calls that were going directly from your software to the root kernel. Almost all that was being virtualized. The system calls themselves were being virtualized, which is a nice kind of security boundary. Containers don't have that. When your applications are making system calls, you're pretty much making system calls all the way back to the host operating system, which does expose you to the risk of breakouts and that kind of stuff. But on the flip side, again, we get really fine-grained controls over the features we can do. There are all sorts of features of the operating systems that allow us to set up very fine-grained controls for application privileges along those shared resources. So again, this one's a little bit of a trade-off. And then finally, one more difference between them from a security perspective is lifetime. Virtual machines looked a lot like the way we deploy physical hardware. We'd kick them up, we'd leave them out there, we'd upgrade them in place, we'd remove and add libraries and software from them during their lifetime sometimes, because it was just kind of cumbersome to move around whole multi-gigabyte virtual machines. And from a security perspective, this had a great benefit, is that if something went wrong, that virtual machine was probably still in a similar state during the attack versus when we were doing our forensics. So later, after we've seen the attack happen and we want to go back and figure out what happened, we can dump the file system that probably has some traces of the event that occurred. So forensics is actually pretty straightforward on a virtualized environment. Whereas in a containerized environment, those containers are going up and down. They're appearing and disappearing all the time. The software gets upgraded as things scale to handle load, which means that it's much harder to do forensics because a lot of the evidence we'd use for forensics might already be gone. But on the flip side, when an attacker is building their kill chain where they bounce from one system to another, those short-lived containers are an impediment to their ability to kind of tunnel their way through your defenses. Because they'll break into a container and then you'll do an upgrade, and without even knowing that somebody's causing trouble, you'll wipe out their container and they'll lose their foothold in your environment. So this one's kind of a flip side, it's kind of a toss-up in both ways. But regardless of all of these kinds of differences in the way that attackers can attack our systems and in the ways that the things we need to watch out for, and the advantages we have, a lot of the practices we need to do to protect ourselves are pretty much the same. So despite a lot of things seeming different superficially, a lot of our old tricks, a lot of our old techniques are going to work fine. It's more the same than different. Okay. So now that we understand kind of the situation we have to deal with, the pros and cons, and the differences between them, let's do some threat modeling. Let's think about the kind of attacks. Let's think like an attacker and try and predict what they're going to do by thinking what we would do in their shoes. This is called threat modeling. So an important part of threat modeling is to kind of break things down into smaller pieces, into different areas, so that we can model those groups of threats separately, so that we can come up with mitigation plans for them separately. So first, or rather, we kind of break down our threats to containers at Google into kind of 3 separate different categories. The first category is infrastructure. So by this, I mean we want to think about the different threats that are potentially going to hit Kubernetes API itself. Like if someone finds a vulnerability in the Kubernetes API itself, and then uses that to infect the applications from the bottom up. Or someone finds a privilege escalation exploit and manages to escalate out of a container and into nearby containers or other systems, or a credential compromise. Another different category of attacks we want to watch out for is supply chain attacks. And these are actually starting to become more common. And essentially this means that instead of going after you and your software developers, instead of trying to phish some of your users, or rather some of your administrators or something, what they're going to do is they're going to look at the source to your web page and find some module that you're dependent upon, or they'll do some OSN, see what libraries you've been patching in the open source. And instead of targeting you directly, they'll target that dependency that you use. Or they'll just they'll kind of guess just by doing random attacks and use and publish vulnerabilities in commonly used libraries to attack you instead. So this is all not your software that you need to worry about. It's the software that you use to build your software, the libraries that go into your applications. So we need to think about that as kind of a separate category that we'll want to try and mitigate separately. And then finally, runtime. And this one is often overlooked with a lot of security strategies because this one isn't about mitigating problems. Not directly. It's not about preventing problems from occurring at all. Excuse me. Instead, it is assuming that something will happen someday. We are going to have an active security event. Some of these are just universally unavoidable. And sometimes they were avoidable, but some of our other mitigations didn't work out. But we need to have some plan in mind for when things do go wrong. Examples of things that you cannot possibly protect against would be a distributed denial of service attack. Like you can put in mitigations in place, but they're going to happen at some point, and you need to have some plan for when that denial of service attack starts coming, when tons of traffic starts flooding you, when all the weird packets come and take down your load balancer. Another thing might be like a node compromise. Somebody has found a vulnerability in your node because maybe your supply chain strategy didn't work well and they found a vulnerability. You need to figure out how you're going to deal with a compromised node, or how you're going to deal with the fact that they escape the container and they get into your cloud project. And then there's always the risk of 0 days. 0 days are new unpublished vulnerabilities, and it's unlikely that somebody's going to burn, like someone's going to spend a 0 day on most of us, because they usually save them for very, very high profile targets, like attacking other governments and things like that. But it is something that definitely can happen. So let's break down. I'm not actually going to spend much time talking about the infrastructure side at all. Instead, I'm going to talk about the software supply chain part and the runtime part in a little bit more detail. So let's zoom on in to software supply chain. So again, this is going to be another story. Story about like how I used to deploy software when let's say I was a startup in like 2010 or so, 2008, 2010. This is how we would release software. Does anyone recognize a release script like this? You spend like a week beforehand going through all the different steps. This is a sequence of different commands I need to run and software I need to deploy. I'd either do this by hand or I'd use this as a requirements document for writing automated deployment scripts. And these would be a whole bunch of things where I go out and I mutate parts of my infrastructure. And by that I mean like I'd run a migration script for my Rails app. Or I would go and I would take servers out of rotation from the load balancer one at a time, patch the software, and then put them back in rotation. That kind of stuff. And this strategy worked for us for a long time. But from a security perspective, it definitely kind of reduced our ability to be nimble. Because what would happen is security vulnerabilities would happen. Security vulnerabilities like Dirty Cow, which was a kernel vulnerability. It was bad. It happened a few years ago. Or Heartbleed, Spectre, etc. And I forgot what I was going to say here. I apologize. Got it. Okay. And the problem with a lot of these vulnerabilities is the vulnerability would come out. I apologize for my flopping on some of my phrases. It's been a while since we're doing this one. Go back to that. So one of the problems we'd run into is these vulnerabilities would come out, and we'd always have the same fire drill over and over and over again. We would have to figure out, were we impacted? Do these cleverly named and beautifully iconed vulnerabilities impact our infrastructure? Because we get an email from the CEO being like, hey, Dirty Cow's in the news, are we impacted? And we'd be like, I don't think so. And what we would do is we end up going back. We'd either log into all the systems individually and start inspecting them to see if we were impacted, which was really time consuming and just a panic every time. Or we could go back to our scripts and we could read them by hand to see if we were impacted. Then we'd write up another script and mitigate it. And this was a huge bummer. But now we live in a world where our deployment scripts look more like this because we're running in a containerized environment, and we have these descriptors for our environment of what it is, which is great because these are not only executable in terms of defining your environment, but they're also parsable. So what you can do is you can write software that reads them for you. So the next time a vulnerability comes up, you can check against things like container registry. And it'll tell you, as new vulnerabilities come out, if any of the images that you're deploying to production are impacted by any vulnerabilities. In this case, I have one up there. It's kind of hard to see. But this one has, I took an intentionally vulnerable virtual machine, or rather, I took an intentionally vulnerable container image, uploaded it to Google Container Registry, and it found 1,325 vulnerabilities, 687 of which have been fixed. So, which is way easier than going through those by hand and trying to figure out what's going on. And then, if I want to figure out which of those 1,000 things I actually need to fix, I can go in and I can see that they've been scored. So what it does is it takes the versions of software from the container image and then checks them against the vulnerability databases that are out there, the CD databases, and gives us instructions, details on, so I can click through and figure out how bad this is. This vulnerability exists on my system. Does this really impact my software? Sometimes the answer is no. Sometimes the answer is removing a library that I don't really need or finding a substitute. And sometimes it's applying one of these fixes. But I get, a wonderful dashboard. And this is Google Container Registry version of it. But there's a lot of other software out there that does basically the same thing. You put in your container descriptors, and it gives you a list of the vulnerabilities from the databases. And then yay. But there's still the risk of people ignoring these notifications. So what you can do is integrate it with the rest of your supply chain. You can set up your build systems. Like in this case, I'm establishing a policy that allows me to restrict the amount of vulnerabilities and severity of vulnerabilities that get deployed to production systems. So this is just, I can use the same programmatic techniques to put something in place to prevent these things from going out into the wild and getting deployed in my software. And I took screenshots of the Google software because it's easier to get it past the layer cats, but there's a whole bunch of different software out there. So if you have a preferred build software vendor, there's probably something that will address your needs here too. But the Google stuff's great too. Okay, so that was a super crash course in how supply chain is made much better in a containerized world. We have parsable, standardized scripts that define our environment. We can actually write software, and the software already exists that does a whole bunch of stuff to see if there are problems. Which is great, because now we can make sure that we don't have bad stuff deployed to software, deployed to production. But sometimes, no matter what precautions we take, bad things may happen. And these are the class of vulnerabilities I call runtime issues. So let's dig into this a little bit deeper. The first question I hear when I bring up runtime security to people is, why bother? I have all these things in place. I talk to my security team. They say things are secure. Well, first of all, it's never really a binary thing. It's always kind of a gradient. Because if the only completely secure server is one, or the only completely secure computer is one that doesn't actually talk to any external systems like people. Instead of trying to focus on, but there's all these things that can happen. Your vulnerability scans might be incomplete. Misconfigurations always happen. Even if you have wonderful container images, if you make a mistake in configuring some production system, like accidentally leaving your dashboard open to the outside world, things can happen. And there's always a chance of people dropping ODays. So rather than try and focus on making just your supply chain thing perfect, a better overall strategy is, instead of building one really tall fence post to block people along one particular path, you want to block them even if they sidestep. You want to build a fence. It's better to spend your energy building a low fence than one really high fence post. So this is kind of the idea of avoiding fence post security. It's better to have more coverage in more areas than a whole lot of coverage on just one. We also call this defense in depth. Okay, so what is the solution to runtime security? The solution is to figure out when an event happens, to figure out that it's happening right away. You want to know as early as possible. So this is going to come back to monitoring software. Yay, software solves our problems again. So I'm going to spend a few slides talking through kind of the different designs that people have taken, the different design approaches people have taken to monitoring containers. Because monitoring containers is a lot different than a typical intrusion detection system you might have in place, like a box inside a network. These container monitoring designs typically will hook straight into the containers themselves. They're going to log a whole bunch of stuff. And by log a whole bunch of stuff, I mean an incredibly high volume of things are going to be inspected. Like we're talking like every system call that goes through the kernel, which is an incredibly high volume of stuff. And then they're going to pass these through different policies around alerts figuring out what kind of patterns to actually ping you about, and and potentially also automatic remediation, which is something we have that was harder to do before that we could do now. Which is, instead of paging you to tell you to go fix the problem, we have the software, when it detects certain events, do something immediately automatically so that we can take action. And then it also has controls for doing some kind of forensics controls later. Because as I said, those containers are probably going to be gone. This is a way to kind of shift that forensics needle a little bit so that we have some signals to look at when the events are done. So as I said, these are really high volume things. So the kinds of things that the monitoring software is typically going to look at is they're going to look at things that are on the order of like every system call that's happening. For example, ptrace, kprobes, and trace points, which are potentially giving us access to that kind of information. Maybe the system audit logs. But there's also, if you're running newer kernels, you can use things like eBPF, which will give you a more efficient view into the same kind of metrics. And there are even some user mode APIs that might be useful here, like iNotify, which can be hooked into to get those events out. But essentially, we're streaming system calls. So people come up with some clever deployment models for how to handle that flow of data, because you can't just log it all out all the time. The way they generally work is you have your containers running on a pod in your Kubernetes cluster. Yay, it's running on a node. You have a system kernel on that node. What they'll typically do is they'll typically deploy a management container to each one of your nodes. And this is a special container that's running in a privileged state. Then that is going to instrument all of your real containers, potentially using a kernel module. So they'll install a kernel module onto the operating system of the node itself, the host operating system. And it'll then send signals down about what kind of events it cares about and turn the filters up and down. Or it could potentially use a privileged container running within each pod to introspect all of the other containers within that pod. But in any case, you have the high volume of stuff coming out of that management container. These are either going to be pre-filtered and then sent to things like a local database, or filtered a little more and sent off to the cloud. Some people have also done really clever things where they have like a ring buffer running on the node itself. And what they'll do with the ring buffer is they'll just feed everything into that ring buffer, and they'll have like a 5-second snapshot of the events that have occurred, because it's super efficient to just keep dumping stuff into that. And then if they detect an event, they'll dump that last 5 seconds of history out to the cloud or something like that, so that you get a snapshot of what just happened leading up to your detection event, which is actually the stuff you probably care the most about. OK, so we have software running now. It can detect an event. We define a bunch of rules. What are we going to do with those rules? What are we going to do with the results? So generally, the approach is you're going to be taking the obvious thing, first thing is if something is going wrong, send an alert. So you're going to write some rules based on the events that you match against a set of events, send a page out in this case, and an email in that case, which is kind of what we're used to from typical intrusion detection systems. But we live in a containerized environment where we can programmatically just apply things to the rest of our environment. There's an API that Kubernetes has that we can use to move containers up and down, set up network policies. And we can totally take advantage of that in our runtime security software too. So another thing you might want to do is if a container is misbehaving, like if it's a web application node, you can just isolate it. You can change the network policies around that node programmatically using the Kubernetes API and isolate it. And now the attacker might not know that they've been isolated. They'll sit there out there trying to enumerate everything around them and be like, oh, this place is really locked down. I don't know how this web server works at all. Which is great, because you might be able to catch them in the act, get more information you can use for forensics later, and at the same time prevent them from pivoting to something else. And then if things get worse, you might want to take a more aggressive action. You might want to pause the container, or restart it, or kill it, if they're starting to get some headway, if they've already had a significant event, and you just want them out. So you can also automatically start killing containers as they get compromised and that kind of stuff. So then, when you finally respond to that alert 3 seconds later, and you pull over in the car, and pop out your MiFi, and finally log in, a lot of the mitigation actions that you would have taken anyway have already been done. So, why are containers special good? Why do we have to take different approaches? Why do we have to install special software? Well, back in the virtualized days, we typically had some intrusion detection system either running on the host or running on the network. And this was very much a host-centric thing. You think about the kind of logs you would see in that system, you'd probably see IP addresses with a bunch of data on them, which is great, because when we have long-lived virtual machines, we could use it. We could trace that back to a specific machine that was running on it, and probably a specific virtual machine, and it was probably still there. But that approach doesn't work as well anymore, and we have to use these container-aware systems because those containers are going up and down all the time. So that IP address will refer to a node, but you may have no idea what pod was actually running on that node at the time the event occurred, because you might be doing forensics days or hours later. So you need something that is aware of the containers themselves. So I just described a bunch of software, and there are a whole bunch of options out there, and honestly, most of the full features things are commercial software out there. So if you have any preferred IDS vendor or anything like that, talk to them to see if they have something container aware, and before you start rolling out Kubernetes deployments, you want to make sure that you have something in place that will work with that. If you're using a managed container runtime, which is a great idea, like Google Kubernetes Engine, there's a whole bunch of partners we have that integrate today. So, and some of these have open source options too, which is what we're going to look at now. So let me show you this stuff in action. Let me bring up my VLC. That's the wrong demo. So let's see one of these in action. Okay, so there we go. Now you can actually see it, kind of. Okay, so here is me on Kubernetes Engine. And I am running a very small Kubernetes cluster. It has a single service running on it. It has WordPress. And WordPress is cool and all. It is a fully up-to-date and patched WordPress, because it's kind of hard to avoid running WordPress every once in a while. But I'm in luck because I thought ahead and I went and got, Sysdig has an open source container security system, a piece of software called Sysdig Falco, which is what I've decided to deploy here because I didn't want to spend any money on intrusion detection software. Sysdig has commercial options too that are more feature rich. This is just the free one. So now we're going to go into, here's our WordPress blog. And this WordPress blog is fully set up, and it is awesome because it's WordPress. And I can hand it over to other people in my organization, and they can use it to run their own, let's say, marketing campaigns. No offense if anyone's in marketing, but I'm gonna be teasing marketing right now. So WordPress is cool in that it's very easy for people to use, but it has one kind of interesting feature, which is no matter how up-to-date it is, if you're an admin on WordPress, you can change the templates. And the templates on WordPress are actually executable PHP code, which is kind of interesting. So if somebody who was doing an update here chose maybe not the strongest password, somebody might figure that out either by doing credential stuffing, like they buy passwords and logins online, find a reused password, and they've now compromised, a bad person has now compromised our WordPress blog. And they put in a single line of PHP code that looks completely innocuous. And now if you go back to, the attacker goes, if anybody goes and hits that WordPress blog, oh, now I'm doing something else. So now down here we have the virtual machine the hacker has set up somewhere else. So they have a command and control server running somewhere else in some other cloud instance. And they're running a little command on that thing. You're running a program called netcat. And if anybody goes back to their WordPress blog, usually the attacker, and in this case, they hit the 404 page, which is where that one line of PHP was hidden, they now have a shell on that WordPress box. So they have the ability to do things like install applications on that WordPress system. And in this case, I'm downloading some cryptocurrency mining software. And I am mining, about to mine. And now I'm attempting to mine some Ether, which this machine doesn't have video cards, so it doesn't work. So that would actually probably have gone unnoticed in most situations. Like the WordPress blog might have been running a little slow, the CPU probably would have been a little high. You might not have noticed for a while. But it's okay, because we actually have runtime security software installed. And what happened is my DynoDraw company security alerts dashboard, which is written in like 5 lines of Firebase code, actually saw that event. And whenever I go and trigger that reverse shell, it's going to show up as another event on there. So this is the kind of thing, I'm just sending an alert to a dashboard right now, but this is the kind of circumstance that I could use to auto-mitigate. Like at that point, I can see details of it. It's a little hard to see in there. But I can see that an untrusted binary was run by www.data user, and it spawned a shell. And then it gave me the command, and it gave me the IP address of the command and control server the attacker used. Like that's a strong enough signal that I would probably do automated mitigation. That should never happen. That's bad. So yay, the day is saved. An event happened, but we detected it early, and we were able to take mitigation steps right away. So let's wrap up. So I've told a bunch of stuff to you. I've described a bunch of software. If you're about to go investigate deploying a Kubernetes in your organization, what can you do today to make sure things stay safe? Well, the first one is think about this stuff before you start pushing Kubernetes to production. Like think about security just a little bit. Like any time you spend there is going to be, half the battle. Write a security plan. Try and focus on covering many areas. Spend a little time on your supply chain. Spend a little time on securing your infrastructure. A good option for the infrastructure security is using a managed runtime. They're great. They patch themselves. If you're going to be using software, try out the open source options for runtime security and others. There are great open source options. If you have a commercial vendor for security software, talk to them about containers and see if they have an opinion. And if there's not a really good solution there, start playing the field before you start deploying stuff to production. The other thing is, no matter what you do, you want to deploy your software early. You don't want to wait for a security event before you start using software to help automate your security. And the reason for that is you want to get some baseline readings. Because when you first install this stuff, like if I first throw Falco on a GKE cluster, there's going to be a bunch of false positive signals that come up from monitoring and stuff like that. And I'm going to need to know, I need to be able to write rules to make sure that those don't trigger events later on. Because they're just going to create tons of noise when things actually happen. It gives you time to tune your signals and make sure that things will actually give you a good signal-to-noise ratio when events occur. And then another thing I'd strongly recommend, not just for Kubernetes security, but security in general, rehearse an event. Pay attention to all of your security monitoring software and other security measures you have in place when you get one of those PCI compliance required penetration tests. Don't just get the report and throw it on your desk. Actually pay attention to your security software to see if you were able to detect that and respond to it accordingly. Or just have your own company hack day where instead of building software, you have some people do a red team exercise and they try and test their own system. This is a great way to learn how to write better software by breaking it yourself, especially when it's your own software you broke. So with that, thank you so much. I know this is not the talk you came into this room for. I hope you learned something anyway. And thank you so very much for bearing with me as I tried to recall this talk, because I did not rehearse it at all.